In the low-lying lands of South Florida, a massive artificial reservoir is gradually taking shape on what was once an endless expanse of sugarcane fields. This is the Everglades Agricultural Area Reservoir. When completed, the project will cover more than 42 million square meters, hold up to 78 billion gallons of fresh water, and become one of the largest above-ground reservoirs ever built in the United States. In this video, join Mandarin Tech as we explore how engineers are building this enormous reservoir. From the underground seepage barrier wall, stretching more than 27 kilometers to the water management system that is helping reshape the future of South Florida's water supply. The EAA Reservoir is located south of Lake Okeechobee and is one of the most significant water management projects ever undertaken in Florida. It is designed to capture excess water from Lake Okeechobee, store it during periods of heavy rainfall, and then move it through an adjacent stormwater treatment area before sending it south to support agriculture and the Everglades ecosystem. With a construction investment exceeding $4 billion, the reservoir has been described as the crown jewel of the Everglades restoration effort. Its importance extends far beyond its size. The project is expected to help restore the natural flow of fresh water across South Florida, improve environmental conditions, and strengthen water security for millions of residents throughout the region. By providing a controlled system for storing, treating, and distributing water, the reservoir delivers long-term benefits for both the environment and the local economy, while helping create a more resilient water management network for future generations. Before construction could begin, engineers first had to prepare and stabilize the ground to create a reliable foundation for the reservoir. The site had previously been used as agricultural land, and its surface was covered by a thick layer of organic soil formed through decades of farming and natural sediment accumulation. Millions of cubic meters of material, including the entire organic soil layer, were excavated to expose the limestone bedrock beneath. This limestone was formed over millions of years and contains countless cracks, cavities, and natural water pathways. In many ways, the rock behaves like a giant sponge. Water can easily move through the fractures and voids below the surface. Without proper protective measures, a significant portion of the reservoir's water would gradually seep into the underlying geological layers instead of remaining stored within the reservoir. In areas that were particularly complex or difficult for heavy equipment to access, workers carried out manual cleaning operations. They carefully cleaned individual cracks and small corners of the rock surface by hand to ensure that no loose material remained that could compromise construction quality. Once the limestone surface had been thoroughly cleaned, engineers began placing a layer of controlled low-strength material CLSM, a material with properties similar to concrete, but with lower strength and superior flowability for filling gaps and voids. This foundation layer provided a more stable and controllable working surface, helping support the entire structure throughout the construction process. Building a reservoir in Florida involves far more than constructing embankments and storing water. Because the underlying limestone is highly permeable, engineers had to build a massive underground seepage barrier wall, stretching for dozens of kilometers to prevent water loss and ensure the reservoir operates efficiently. The structure is approximately 27.8 kilometers long and extends as deep as 18 meters below ground. It is considered one of the largest underground seepage barrier walls ever constructed for a freshwater reservoir in the United States. Construction began with the excavation of deep trenches along the entire planned alignment. However, digging trenches of this depth presents a significant risk of collapse. To address this challenge, engineers continuously pumped a specialized bentonite slurry into the trench throughout the excavation process. This slurry exerted pressure against the trench walls, stabilizing the surrounding soil and preventing cave-ins before construction could be completed. In areas where the limestone bedrock was particularly hard, construction crews used powerful trench-cutting machines capable of slicing through solid rock formations. Once completed, the seepage barrier wall functions like a gigantic underground dam hidden beneath the surface. By reducing water losses, improving the efficiency of reservoir operations, and helping maintain long-term water storage capacity. The structure plays a critical role in securing a reliable water supply for the region's future. Once the foundation and seepage control system were completed, the next stage was the construction of the embankment surrounding the reservoir. Instead of relying solely on traditional borrow pits and external material sources, contractors used large draglines capable of excavating material from below the water table. After being brought to the surface, the material was allowed to drain naturally before being transported to on-site crushing and screening facilities. There, the soil and rock were crushed, sorted, and processed to meet strict engineering specifications. Dump trucks then carried the material to the embankment construction zones, where bulldozers spread it into carefully controlled layers. Large vibratory rollers compacted each layer, and no additional material could be placed until the underlying layer had met all required standards for density and stability. The next major task was the construction of the reservoir's water supply and discharge canal network. Millions of cubic meters of earth had to be excavated to create these channels. The canal banks were reinforced to withstand erosion under high-flow conditions and ensure long-term operational reliability. In addition, a water recovery canal was constructed along the northern boundary of the reservoir. This canal serves as a backup collection system. If any water escapes around the seepage barrier system, it can be captured by the recovery canal and redirected back into the reservoir network rather than being lost to the surrounding environment. One of the most distinctive features of the EAA reservoir is its approach to water treatment through the Stormwater Treatment Area STA. Rather than relying entirely on complex mechanical systems or large quantities of chemicals, the project uses natural processes to improve water quality before it is released back into the Everglades. The result is a solution that combines modern engineering with the natural cleansing abilities of wetland ecosystems. The treatment process begins when water from Lake Okeechobee or surrounding canals is diverted into the STA. Once inside, the flow is carefully controlled and directed through a series of large treatment cells covered with aquatic vegetation such as grasses, cattails, reeds, and other native wetland plants. Maintaining a slow flow rate is critical because it allows biological processes to operate more effectively. As the water moves through the treatment area, aquatic plants absorb phosphorus and other excess nutrients. At the same time, microorganisms living in the soil and around plant roots help break down or transform a variety of pollutants. Some nutrients become stored within the plant biomass, while others settle to the bottom or removed through natural ecological processes. Working together, these mechanisms significantly reduce phosphorus concentrations before the water continues its journey southward. Florida has used the STA concept for decades and has achieved substantial improvements in water quality across the Everglades watershed. What sets the EAA reservoir apart, however, is its enormous scale. Thousands of acres of wetlands have been designed and operated as a vast natural filtration system capable of treating large volumes of water every year. By combining storage and treatment within a single integrated project, the EAA reservoir helps deliver cleaner water to the Everglades while supporting the long-term restoration of one of America's most important ecosystems. Once completed, the EAA reservoir will function as a massive water management system, serving as a key component of South Florida's water regulation and Everglades restoration strategy. During the rainy season, when water levels in Lake Okeechobee rise and place increasing pressure on the region's flood control infrastructure, high-capacity pumping stations will divert excess water into the EAA reservoir for temporary storage. When operating conditions are appropriate, water stored in the reservoir will be released into the adjacent Stormwater Treatment Area STA. There, it will flow slowly through engineered wetlands designed to remove much of the excess phosphorus and other nutrients before the water continues downstream. After meeting environmental standards, the treated water will be conveyed south through a network of canals, water control structures, and other restoration projects. From there, it will continue toward the Everglades and eventually Florida Bay, helping restore a more natural pattern of freshwater flow across the region. This operating system provides several important benefits. By capturing and treating excess water before it reaches the coast, the project can significantly reduce nutrient-rich discharges into estuaries and coastal waters. At the same time, the additional flow of clean freshwater helps replenish South Florida's groundwater resources and slows the advance of saltwater intrusion, a growing challenge for many coastal communities. Through its ability to store, treat, and strategically distribute water, the EAA reservoir is expected to play a vital role in improving water quality, strengthening water security, and supporting the long-term health of the Everglades ecosystem. To understand why Florida decided to invest billions of dollars in the EAA reservoir project, we first need to look at how the region's natural water system has changed over the past century. In the past, after each rainy season, excess water from Lake Okeechobee slowly flowed south through the Everglades, one of the largest wetlands in the world. This water spread out in a shallow sheet, moving slowly through marshes, grasslands, and swamp forests before reaching Florida Bay. Along the way, it also recharged the Biscayne Aquifer, the main source of drinking water for millions of South Florida residents. However, as the population grew rapidly during the 20th century, an extensive network of canals, levees, and pumping stations was built to control flooding, expand agricultural land, and support urban development. While this system allowed people to use the land more efficiently, it also disrupted the natural flow of water. Instead of continuing south, much of the water from Lake Okeechobee was diverted east and west before being discharged into the ocean. This has been one of the factors contributing to harmful algal blooms and declining water quality in coastal estuaries. Meanwhile, the Everglades began to suffer from widespread wetland degradation. Habitats for native species shrank, and the ecological balance was gradually disrupted. At the same time, rising sea levels increased the risk of saltwater intrusion farther inland, threatening the water supply of approximately 5 million residents. For this reason, the EAA reservoir was built to store excess water from Lake Okeechobee instead of releasing it directly into the ocean. The water can then be treated and redistributed according to the needs of the ecosystem and the regional water management system. Although it is considered one of the most ambitious environmental restoration projects in the United States, the development of the EAA reservoir has not been without challenges. When the project was approved in 2000, the original completion date was set for 2034. However, due to the continued degradation of the Everglades and growing pressure on regional water resources, Florida officials pushed to accelerate the schedule. Following an agreement between the state of Florida and the U.S. Army Corps of Engineers in 2025, the target completion date was moved forward to 2029. Accelerating construction will allow the system to begin delivering benefits sooner, but it also creates significant demands in terms of quality control, funding, and project oversight. Some conservation organizations have expressed concerns that a faster schedule could reduce the time available for evaluating the environmental impacts of certain project components. Experts have also warned that any major changes to the Everglades water flow system must be carefully monitored to avoid unintended consequences for the ecosystem. Another issue that generated considerable debate was a proposal to develop an industrial rock mine near the reservoir site. Scientists raised concerns that blasting and large-scale mining activities could affect the underground seepage barrier system and increase the risk of water leakage in the future. After years of legal disputes and public debate, the scale of the mining project was significantly reduced. In recent months, whenever tensions in the Middle East rise, a nearly 200-kilometer sea route immediately becomes the center of global attention: the Suez Canal. If traffic through this corridor is disrupted, the journey between Europe and Asia can become thousands of kilometers longer, as ships are forced to sail all the way around the Cape of Good Hope at the southern tip of Africa. This shows that the artificial canal cutting across Egypt's desert is not just a transportation route, but a strategic artery of global trade for more than a century and a half. But to create a shipping corridor that now looks almost natural on the map, humans had to dig through a strip of land connecting two continents under conditions where there was almost nothing except sand and wind. So how was this massive project actually built? Join Mandarin Tech as we uncover the answer right now. Stretching more than 190 kilometers across the Egyptian desert, the Suez Canal is one of the most ambitious engineering projects ever built to reshape how the world moves across the oceans. Since it first opened in the 19th century, this artificial waterway has allowed ships to travel directly from the Mediterranean Sea to the Red Sea without having to sail around the entire continent of Africa, a detour that once added tens of thousands of kilometers to the journey. Today, around 18,000 ships pass through the canal each year, transporting nearly 700 million tons of cargo, including massive vessels up to 400 meters long and weighing as much as 240,000 tons. However, to keep up with the ever-growing size of the global commercial fleet, the canal has never truly been finished. Over more than 150 years of operation, it has been continuously deepened, widened, and restructured, from manual desert construction sites in the 19th century to a massive dredging project completed in just 1 year in the early 21st century. Looking at a map, many people assume the Suez Canal is simply a straight waterway cutting across the Egyptian desert, but in reality, its shape changed significantly during the massive expansion project between 2014 and 2015. In less than 12 months, Egypt excavated an additional parallel channel about 72 kilometers long along the northern section of the existing canal. The goal was not only to widen the canal, but to completely transform how ships move through the Suez route. Before the expansion, most of the canal still operated as a one-way transit corridor. Ship convoys had to take turns passing through and stop at designated waiting areas to allow traffic from the opposite direction to pass. As a result, the average waiting time could reach up to 11 hours, while the total transit time through the canal often approached 18 hours. After the parallel channel became operational, ships were able to travel in both directions simultaneously along a much longer stretch of the canal. This reduced the average waiting time to about 3 hours and shortened the total transit time to roughly 11 hours. To make this possible, dozens of high-capacity dredgers had to operate continuously in desert summer conditions exceeding 40 degrees Celsius, removing around 250 million cubic meters of material, while the original canal remained fully operational throughout construction. This is what turned the 2014 Suez expansion into one of the most complex construction while operating maritime engineering campaigns in modern history. To excavate a canal tens of kilometers long in less than a year, engineers could not rely on conventional land-based excavation methods. Instead, most of the work on the Suez construction site was carried out by a specialized fleet of dredging vessels known as cutter suction dredgers. At the front of each vessel is a rotating metal cutting head that continuously breaks up the soil and sediment on the canal bed. Immediately afterward, a high-capacity pumping system draws the mixture of water and loosened material into the vessel, creating a slurry that is transported through pipelines stretching several kilometers to disposal areas or land reclamation zones. Thanks to this method, the excavated material did not need to be transported by trucks like on a typical construction site. Instead, the entire volume of dredged soil was moved directly by water flow itself, allowing construction speed to increase significantly. In many sections of the Suez expansion project, the excavated material did not even leave the construction area. It was pumped directly to both sides of the canal to form artificial embankments that helped widen the navigation corridor. In addition to cutter suction dredgers, trailing suction hopper dredgers were also used to remove material from the canal bed while moving continuously, then transport it to disposal sites located farther away from the construction zone. The coordination between multiple types of dredging vessels created a nearly uninterrupted construction workflow operating around the clock. Completing a project that was originally expected to take several years in just 12 months, while still keeping the canal fully operational, was one of the biggest engineering challenges of the 2014 Suez Canal expansion. Instead of shutting down the canal during construction, engineers had to organize the entire site so that construction and navigation could continue at the same time. Dredging vessels worked within tightly controlled zones to avoid interfering with commercial ships passing just nearby. Because of this, the maritime traffic coordination system had to operate with near-perfect precision to ensure safety for both shipping traffic and construction equipment. At the same time, the construction site was divided into multiple independent working sections so that dozens of dredging vessels could operate simultaneously. Rather than following the traditional step-by-step construction sequence, the project adopted a large-scale parallel construction model, allowing many segments of the new canal channel to be excavated at the same time. To maintain this pace, equipment had to operate around the clock under harsh desert conditions. During the day, crews worked in extreme heat and hot winds blowing from the Sinai Desert. At night, operations continued under massive construction lighting systems, stretching across tens of kilometers along the canal corridor. If the 2014 Suez Canal expansion project was a modern engineering campaign, supported by fleets of high-capacity dredging vessels operating continuously day and night, then the original construction site in 1859 began under conditions that are almost difficult to imagine by today's standards. When the first excavation work began, the region had no proper transportation routes for construction materials. There were no ports capable of receiving heavy equipment. There was no stable supply of fresh water to support a large workforce working for months under harsh conditions. Most importantly, there were no large mechanical excavation machines capable of cutting a canal nearly 200 kilometers long through constantly shifting desert terrain. Engineers at the time were attempting a task that had never been carried out before on such a scale. As a result, the early stages of construction relied almost entirely on manual labor. Workers used picks, shovels, and simple hand tools to dig through layers of sand. Excavated material was placed into small baskets and then carried away by hand or transported by animals such as donkeys and camels. Under extreme desert temperatures, strong hot winds, and limited shelter, excavation progressed very slowly and required enormous physical effort from thousands of laborers working continuously along construction zones stretching for dozens of kilometers. Fresh water quickly became one of the most serious challenges facing the project. Maintaining a large workforce in the middle of the desert was impossible without a reliable water supply. To solve this problem, engineers launched a parallel infrastructure project, building a freshwater canal from the Nile River to the Suez construction site. This canal became a true lifeline for the entire operation. It provided drinking water for tens of thousands of workers, supported the formation of temporary settlements along the construction corridor, and created the logistical foundation that allowed the project to continue operating in such a harsh desert environment. At the peak of construction, it is estimated that up to 400,000 workers were brought to the site to dig soil, transport materials, and widen the canal using simple hand tools. They worked under extreme heat, with limited access to drinking water, and almost no protective equipment by modern safety standards. Working conditions were physically demanding and often dangerous, especially across long stretches of open desert terrain. In 1864, when the system of forced labor was abolished under strong international pressure, the Suez construction site immediately faced a serious labor crisis. Hundreds of thousands of workers left the site almost at the same time, putting the entire project at risk of coming to a complete standstill. This sudden loss of manpower forced engineers and project leaders to urgently search for alternative solutions to keep construction moving forward. At that moment, a critical question emerged. If there were no longer hundreds of thousands of manual workers who would continue digging the canal, the engineers' answer was not to recruit more workers, but to completely change the way the project was built. A decisive turning point followed: the full mechanization of the construction site. Large numbers of steam-powered excavation machines began arriving in Egypt from Europe. These were among the first large-scale canal digging machines ever deployed on an infrastructure project nearly 200 kilometers long. Unlike manual labor, which could remove only thin layers of soil each day, these machines could operate continuously for many hours and produce several times more output. As a result, construction progress increased significantly within a short period of time. Mechanization did not only make excavation faster, it also allowed engineers to control the shape and depth of the canal channel with much greater precision. This level of accuracy was extremely important for a maritime route stretching hundreds of kilometers and requiring a stable and consistent gradient along its entire length. Even after steam-powered excavation machines began replacing manual labor at the Suez construction site in the late 19th century, a series of major engineering challenges continued to threaten the progress of the entire project. Most of the canal route was built across loose sand layers and weak sedimentary ground. As excavation went deeper, the canal banks became highly vulnerable to collapse, especially in areas affected by strong desert winds or seasonal water level changes. This forced engineers to continuously adjust the slope geometry along both sides of the canal to ensure long-term stability, rather than treating excavation as a one-time operation that ended once digging was complete. In other sections, the construction route passed through natural depressions and lake regions, including areas that later became part of the canal system itself. In these locations, construction was not simply about removing soil. Engineers also had to carefully manage water levels in order to transform existing natural lakes into integrated sections of a continuous navigation corridor, linking the Mediterranean Sea with the Red Sea. It was the ability to solve these geological, hydraulic, and logistical problems simultaneously that allowed the Suez construction site to maintain progress under conditions that many 19th century engineers had once believed made the construction of an intercontinental maritime canal across the desert nearly impossible. When the Suez Canal officially opened in 1869, many people believed the world had just completed one of the greatest infrastructure projects in history. But in reality, that moment was only the beginning of a megastructure that has never truly been finished. Soon after the canal entered operation, the size of global ships began increasing faster than 19th century engineers had originally expected. This forced the canal to be continuously deepened, widened, and geometrically adjusted over the following decades. Without these regular upgrades, the Suez Canal would likely have become outdated after only a few generations of commercial vessels. Throughout the 20th century, the canal was closed several times due to wars and regional crises, especially after the 1956 Suez Crisis and later conflicts in the Middle East. At certain periods, traffic through the canal was interrupted for several consecutive years, turning what was once a major global shipping corridor into a strategic bottleneck in international trade. Even in the modern era, the Suez Canal continues to prove that it is a structure that can never remain unchanged. The grounding of a massive container ship in 2021 temporarily blocked the entire waterway for just a few days, but that was enough to disrupt global supply chains and push engineers to continue adjusting the canal's navigation geometry at several critical sections. For more than 150 years, the Suez Canal has functioned as a living piece of infrastructure. It has been continuously deepened, widened, and reshaped to adapt to the ever-growing size of ships in global trade. If this corridor, less than 200 kilometers long, is disrupted for just a few days, global supply chains can immediately begin to shake. That is why whenever tensions rise in the Middle East, the world once again turns its attention to the Suez Canal. But what is even more remarkable is this. After more than a century and a half of operation, the canal has never truly been finished. It continues to be deepened. It continues to be expanded. And in the future, it will very likely continue to change again and again in order to keep pace with the increasing size of the ships that humans themselves are building. So in your opinion, over the next 50 years, how much more will the Suez Canal need to change to remain the most important maritime route on the planet? Let us know your thoughts in the comments below.